Okay, so next video, we just talked about a refrigerator. Okay, I'm drawing this with you, so you can draw this in your notes as you go along. This is, and I'm as usual, I'll make these PowerPoints available to you guys. Okay, so if we look at, what have I got here? I should have looked ahead. Okay, let's talk about the first law for this thing. I don't have that in the slides, so let's talk about it here. Again, closed system. So if we look at the first law for this closed system, your refrigerator is a closed system. This is, should have put the heading up here. This is a refrigerator. See if I can spell it this time. This looks okay. Refrigerator. First law for a refrigerator. Well, add the ins, subtract the outs. Just the energy. I've got it all labeled here. I've got QL going in. That's the heat coming in from the low temperature source. We're removing heat from this cold space to refrigerate it. I'm also going to put some work into my compressor. Now I've got to reject all of that energy to a high temperature reservoir. It's a closed system, so that's equal to M delta U, the change in energy for the system, and because it's a cycle, in a cycle, the thing's going to return, its final state should return back to its initial state. So that tells me that the work that I put into this thing is equal to basically the heat the net heat that's going out, the difference between QH and QL. Right? Okay. Now, and so when we talk about the efficiency of a refrigeration cycle, we can't call this an efficiency because of the quantities involved here. But it's similar to an efficiency because it's still what we want, the performance of it, divided by what we have to do to get it. The reason we don't call this an efficiency is because this quantity can, and often does, exceed a value of 1. If anything that exceeds a value of 1, we don't call an efficiency. It's just kind of a rule. So, since this value can exceed 1 and often does, we call it a coefficient of performance, a COP. The COP for a refrigeration cycle, COPR, okay, that is the coefficient of performance. Coefficient of performance for a refrigeration cycle is still going to be what we want. We want a refrigeration cycle to remove QL. To get it, we're going to have to put a little bit of work in at the compressor. This guy. Now, if I substitute this in here, because my first law tells me that work in is equal to the difference between QL or QH and QL. So if I substitute this in here, divide everything by QL, it's kind of a weird thing to do, right? Well, it is. But notice what happens if I do that. If I divide everything here by QL, I get this interesting quantity. I get 1 over QH over QL minus 1. Why would I do that? Well, it's going to be important later. Remember I did that with the heat engine. This is the efficiency, what we call the thermal efficiency of the heat engine. We said I can get that down to a function of a ratio of the heat transfers. And I can do the same thing with a refrigeration cycle. I can get this down to a function of the ratio of the heat transfers. And again, that's going to be important probably in the next lecture. We'll see why that's important when we talk about Carnot cycles. But here's the basic idea here. And I think that's what I've got. We can go quickly through this. Yeah, there's our first law. Simplifies down to this. So that means our COP can simplify down to that. You see the algebra here, why we know that's true. Okay? All right. Now, let's talk about a third device. So 2 devices so far. We've talked about an engine. We've talked about a refrigerator. Let's talk about a third device. That's a heat pump. Now, here's the idea of a heat pump. Whenever you walk beside, like if you've got a a window air conditioner unit, that's a refrigerator. A window, any kind of air conditioner is a refrigerator. If you walk by the outside portion of a air conditioner, what do you feel? You feel heat, right? You feel heat coming off of that. And the same thing if you've got a big cooling tower for a central air unit. You got this big hunk of metal that's got a fan in it and it's blowing hot air out, right? That's the same idea. Well, for a heat pump, somebody looked at those and said, you know, it's putting out heat into the outside during the summer. What if we turn that around in the winter? In the wintertime, we want heat inside. So what if we just turn this thing around in the winter and we heat the inside by cooling the outside in the wintertime? That's the idea of the heat pump. It does exactly that. Instead of, it's the same exact cycle, right? We'll draw this quickly. The only difference is we change what we're trying to do with it. So 5 is a heat pump. So 5 is a heat pump. The idea of a heat pump, you still have this compressor. Right? I'm not even going to label these because it's the same process we just saw. Draw it if you like. That compressor is going to increase the pressure and temperature of that refrigerant so hot that it's going to actually lose heat to the high temperature source. You're still going to run it through this expansion process. Somehow we've got to drop the pressure and the temperature, because what we want to do is through this expansion process we want to get the temperature so low then that it will actually, the refrigerant is colder than the low temperature source. In the case of a heat pump, that's probably the outside air. And then we repeat the cycle. So it's the same exact device. In fact, your fancy heat pumps, they're actually a lot of times designed to where they run one direction in the summer to refrigerate, to air condition, and they run the opposite. They flip it around and run the refrigerant in the opposite direction in the winter, so it'll actually move heat into the house. Okay. First law looks the same. We've still got work in minus QH plus QL. That's equal to 0 because it's a cyclic system. So still have work in is equal to QH minus QL. That's the first law. The COP, the coefficient of performance for a heat pump, is a little different, because with a heat pump what I want is I want QH. That's my goal. To get it, I still have to put work in. And if I substitute this in, that's QH over QH minus QL. Divide everything by QH, I get 1 over 1 minus QL over QH. Okay? All right. Now, why in the world would we do this? Well, think about this. Where I live, I don't have good access to natural gas or any other kind of heat source, so I use electricity as my primary heat supply. Now we've actually put in a fireplace in the last few years, so I can actually use a fireplace. But let's say I don't have any firewood, and I just need to generate heat for my house in the wintertime. If I don't have access to any other way, I'm going to have to use electricity. So if I want 7 kilojoules of energy in my house as heat, I'm going to have to pay for 7 kilojoules of energy from the electric company, right? But if I've got this fancy device, I can say, you know what? I can put 2 kilojoules of electricity into a compressor, use that to power this heat pump cycle, and that 2 kilojoules then I can use in the evaporator. I can remove 5 kilojoules of heat from the outside air. And I can take that 5 kilojoules and the 2 kilojoules of electricity, I put those together, and I can put 7 kilojoules of electricity into my, or of heat, not electricity, of heat into my house. I only have to pay for these. Whereas if I'm using an electric heater, I've got to pay for all that electricity. With a heat pump, this is all I got to pay for. This I'm just borrowing from the outside, right? move this heat from the outside to the inside, it's going to propagate back out. You're going to lose heat back to the walls. It's going to go back outside, but it's going to keep the house comfortable for a significant period of time. All right? Now that's a good solid, we'll pick up here next time. That is a good solid start on, that's pretty much the theory. We're at the point now where we can work some example problems, and that's normally what I would do on the next lecture. So let's stop there. I'll see if, let's plan on the next lecture being, we'll focus on some examples, and then probably talk about the Carnot cycle. Loud pop here.